What's up, everybody? Time for free response number 4, 2018. Let's jump right in. Got my favorite shirt on. There it is. Rocking a little Ellen. And that's more important than anything you're going to learn in the next 20-ish minutes. But that being said, let's jump in. Friday's the big day. Best way to get ready for this exam, practice. Practice free response this year. Another year, practice free response, multiple choice. But we got our 45-minute Corona exam to get ready for. So free response nonstop. Let's go. Let's go. Let's go. All right, here we go. So number 4, 2018. Hopefully you've read this. If not, pause it, read it, try it. All right, assuming you've done paused it. So as we read through here, isn't it, pretty standard, I guess, like medical context here, your example of how we could use some stuff. So we've got the ACLs, one of the ligaments that can help stabilize the knee. We're looking at 2 different surgical procedures to try to reduce the recovery time. We've got a standard and a new procedure. So to test the effectiveness of the new procedure, the study was conducted with 210 patients who needed surgery. They were randomly assigned to receive either the standard or the new procedure. And so A asks, based on the design of the study, would a statistically significant result allow the medical center to conclude the new procedure causes a reduction in recovery time compared to the standard for patients similar to those in the study? And then B, summary stats on the recovery times are given here. We've got some sample sizes, mean standard deviations. Do the data provide convincing statistical evidence that those who get the new procedure will have less recovery time on average than those who get the standard procedure? So let's jump in. Part A. Although for a lot of us on the exam, a lot of us feel comfortable with this kind of thing, whatever that means. We'll jump when we get to part B. But so realistically, some of us, right, like if I were doing this, maybe I start with part B, right, whatever. We're all different. Just want to emphasize it's not always the best idea to do everything in order, right? I'm doing everything in order in the videos, just right to kind of go through each step. But on the actual exam, right, read everything, start with what you feel most confident about first. Anyways. So when I read A, one word jumps out at me, and hopefully a word jumps out at you too. And they're asking us, can we establish, right, can we determine that the new procedure causes a reduction in recovery time compared to the standard procedure? So this jumps out at me because one thing we want to keep in mind is if we're trying to decide, can we establish a cause and effect relationship? The only thing that matters is how the data was collected. So a lot of times when I've done this problem, I see students, they see this with a statistically significant result, and maybe they try to like get the p-value and look at how low it is and base it on numbers, or sometimes with cause and effect with scatter plots, students will try to look and see if the correlation was super strong, right? And those are all things you want to stay away from. Like this doesn't really matter. For us, if you're asked if you can establish a cause and effect relationship, if you're asked if one thing causes another, or can we conclude that, all that matters is how was the data collected. There's only one method of data collection that allows us to establish a cause and effect relationship, and hopefully we're all yelling at our computer screen, experiment. And so that's it. That's all we want to consider. To answer part A is how was the data collected. I always like to reword the question with my phrasing. So that's what you're seeing here, right? I'm just rewriting what I'm going to underline in purple, right? So a statistically significant result, that's not purple, a statistically significant result would or would not allow the medical center to conclude that the new procedure caused a reduction in recovery time compared to the standard for patients similar to those in the study. Right? I know that's tedious, I know that's long, but one way to never avoid a mistake with the context is to take that exact context out of the question, right? If we reword it, maybe we leave out the patients to those, similar to those in the study, right, whatever. It'll only take like 15 extra seconds to write all those words. So here, think, was this an experiment? And hopefully you're saying yeah. So for us, we're going to say a statistically significant result would allow the medical center to conclude the new procedure causes a reduction in recovery time. Now, we're not just going to say because this was an experiment, right? We need a little more than that. We need some context, and we needed to show how we know this was an experiment. So our reasoning is because patients were randomly assigned to receive either the standard procedure or the new procedure, this was, or right, the data was obtained by or from or through an experiment. I know I got some typos in there. Happens. So notice I didn't just say it's an experiment. I'm showing like, how do we know it was an experiment? Because there was a random assignment of treatments. Beyond that, I didn't just say there was random assignment of treatments, right? I wanted to add some context, what was randomly assigned. And then the last thing to notice is, right, all I just did was write this. Patients were randomly assigned to receive to the standard, right? So again, use that strategy of taking that wording. I think that's it, I hope. Let's check out the rubric. So to get essentially correct, states it is reasonable to make a causal conclusion, right? We did that with our initial rewording of the context, right? It would allow us to establish that. Justifies based on random assignment of patients to procedures, got that. Or stating a randomized experiment was conducted. Yeah, we did both of those, and then includes context, right? Which is when I said assigned to standard or new procedure. So we definitely have an essentially correct here, right? That's it, one sentence. And most of those words I just copied right from the question that was given to us. You can pause and read through the rest of this rubric. I'm just trying to see what, there was one thing I wanted to point out. Notice you get partially correct if you didn't have the word randomized in there, right? So we had to comment on the, right, like without the word randomized partially, right? We had to comment on random assignment of treatments or a randomized experiment. One thing, right, we want to be concise, just answer the question. So notice here, right, if you talk about all this other stuff that doesn't really matter, those are extraneous. But if those extra things are incorrect, that knocks your score down. So right, in general in the exam, as we've talked about, right, just answer the question, be done, move on. Extra stuff isn't going to make your score better, but it could make your score worse. And that's it. So jumping into part B. So part B here, hopefully we can easily recognize we have two samples, right? We've got the standard group, the new group, two different sample sizes. And we want to know if the data provide convincing statistical evidence. So when we're taking the AP exam, hopefully this phrase, convincing statistical evidence, jumps out at us. So this could be answered with a confidence interval, right? But when we see that phrase, that's telling us to do some kind of hypothesis test. Now there's no p-value given. I'm sorry, my bad. There's no alpha level given, which makes me think the p-value might end up being really low, so anyone would reject the null, or really high, so everyone would fail to reject the null. I don't know if that's the case. We'll produce those values, but that's something that I'm immediately thinking about, right? That doesn't have to be the case, but that's something that I'm thinking about. So we know we need some kind of hypothesis test. That's our convincing statistical evidence. We've got two samples, so it's some kind of two sample thing or two prop thing. We're talking means. So this is our two sample t-test. Right, we're never really going to use the two sample z-test on a free response. That would be if we knew the sigmas, but if you don't know what I'm talking about, just pretend I didn't say that. So we got to do our two sample t-test. So let me hop over to the whiteboard so I don't have to try to type these hypotheses. At this point, that seems pretty unnecessary for me to have copied all that. But anyways, I'm just going to erase it. I'll leave the numbers. So we need our two sample t-test. Somewhere we have to name the type of test or interval. Many of us do that when we copy our calculator screen, but maybe for some of us, we just want to title it right at the top, right? That's not a bad idea. So step one, hypotheses. 4 steps we hopefully know. Every hypothesis test, same 4 steps, right? Hypotheses, conditions, math, conclusion. So here, right, we're talking about means, and we've got two means. We're always going to assume no difference. So we're always going to assume the true mean recovery time for group 1 is the same as the true mean recovery time for group 2. If we're going to use 1s and 2s, we have to make sure we identify which is 1 and which is 2, which is simplest putting a 1 or 2 next to those things, right, on the table. Right, I could give a key. 1 is standard, 2 is new. Or I could just do like mu s equals mu n and then take away that 1-2 situation entirely. Just keep in mind that your calculator is going to have all 1s and 2s. So our question asked, now I do regret erasing all of that stuff. Our question asked if there was evidence that those who get the new recovery will have less recovery time on average than the standard. So we want to know if this new is less than this standard. Or in other words, right, we want to know if mu1, which is the same thing as mu s, is greater than mu n. Oh, sorry, the way I did it over here, this would be a 2 over here, mu n. So maybe for us, right, like maybe with the S's and N's, it's easier to see that the nu is less than the standard. Maybe with the 1s and 2s, maybe that's not as clear. But again, the 1s and 2s are what we're going to see on the calculator. So that's why I like that. I could have also written like mu. I could have written mu n less than mu s. The reason I don't like to do that is because like this is my group 1 and this is my group 2, and that for my null. But then like this is my group 2 and then my group 1 and my alternative. So that's backwards. So I would not recommend doing that, right? But the idea is correct on paper, but I would be worried that some people would mess up their p-value and their alternative hypothesis in the calculator. Lastly, sure, if I wanted to, right, this is not my preference, which is why I don't do it first, but it works, right? I could say mu1 minus mu2 equals 0, or mu s minus mu n equals 0. And then for my alternative, I'd have mu1 minus mu2 is greater than 0, or mu s minus mu n greater than 0. And the reason it's greater than 0 is if the new procedure has a lower recovery time, a bigger number minus a smaller number is going to give us a positive difference, which has to be greater than 0. So that's why, right, it's greater than 0. So we're literally assuming there's no difference in the null when we write it this way. Maybe it's easier to see that like conceptual idea with the blue notation. I don't know, maybe not, whatever. Those are all the ways you could do it. You pick one that works for you, just get it right one way. So hypotheses, done. All right, hopping back over here. Next up, conditions. It's a tedious part. I really wish that it said assume all the conditions were satisfied. This is, you know, this is kind of a long one with the part A and B, but it doesn't. So we got to check the conditions for both groups. Do that right now. Do it. Do it. So all patients were randomly assigned to standard or new. There's our randomization. Recovery times are independent because treatments are randomly assigned. That's our independent groups. Both samples are large enough, right? With means, remember, we don't check like success failure because there's no p-hats, there's no p's. So it's just large enough samples. Right? There's no way we could check histograms. We don't have that information. And then our 10% condition. 110 is less than 10% of all people who get the new procedure. I'm sorry, the standard procedure, probably. 100 is less than 10% of all people who get the new procedure, like probably, right? We don't know that for sure, but we can be pretty confident. So those are our conditions. And then moving forward, we go to the math. That next slide is going to be for the conclusion. So we need our p-value. But math-wise, I'm going to hop back over to the whiteboard. I think I just paused recording and hopefully didn't mess everything up. But anyways, so now we're going to the calculator, right? So math section, we're just going right to our calculator. And I did have all these numbers written down ahead, but you know, I figured it would be good to look at it on the screen. So stat tests, we're talking about number 4 here, our 2-sample t-tests. We're not putting in the raw data, we're putting in the summary statistics, right? There's all those 1s and 2s. That's why I like to notate that up or whatever, label that up here so I don't mix anything up. So X bar, the mean for group 1 as my standard, that's 217. SX 1's 34, N1's 110, second mean 186. Second standard deviation 129, and for the new procedure, sample size is 100. And we want group 1 standard to be bigger than new, right? We want the new to have the lower recovery time. So there's that mu1 less than mu2. We're always going to pick no for these t things. And then we can go to calculate. Copy your calculator screen. Copy your calculator screen because then you will never forget to name the test or interval. Now, of course, if you already wrote that as a title at the start of a free response, you don't do it again, right? That's your, like, backup plan, right? Just copy the screen. I could copy everything. Sure, that's fine. Like, this is my alternative, though, right? So I already wrote that down. So we need our t-score, which is pretty high. And we need our p-value, which is 1, which makes me think I did something wrong. And then we need our degrees of freedom, 207.18. So let's pause here and see that 1's making me uncomfortable. Oh, I'm sorry. Stat tests. hopefully you noticed my mistake, right? I could stop and remake this video, but it seems like it would be more valuable for you to now consider what my mistake is. And just to think about the fact that what made me think I made a mistake is the fact that the p-value is 1. That seems kind of weird. That means I'm shading the whole model, right? So this is what makes me realize I have a mistake, right? This is good. This could happen on the exam for real, and you have to be able to check your own errors. I did this on purpose. Anyways, back to our alternative. When I go to number 4 here, stat test number 4, right? If the p-value seems weird, right? Like the only thing, I just make sure, did I put all these numbers in the right places? Yes. But we want, right? We want standard to be to be greater than new. We want 1 to be greater than 2 based on my stuff up here. For our alternative hypothesis, u standard greater than mu new. And so my alternative on here is backwards. It's like a real class almost, like minus all the students and fun and laughing and jokes. Distance learning is horrible. I miss you guys, but anyways. All right. So now we go to calculate, and we get a p-value that is insanely small, right? It's like essentially 0. If one direction the p-value is 1, the other direction is going to be essentially 0. That's something to think about there. But that kind of jives with my original. Hold on one sec, bud. Idea that the p-value is going to be absurdly low or high. All right, go ahead, bud. Say hi.
Hi.
Say good luck on your exam.
Good luck on your 9%.
What do you got? Show them what you got. What is that?
The turtle car.
Ninja Turtle car. All right.
No.
You could go pee-pee, bud. You don't need my help. Okay, so let's finish up here. So back over to the whiteboard. Like, this is pretty good. Like, I'm not gonna lie to you. You got degrees of freedom, test statistic, p-value. I like to personally label this as p-value, not just p, but right, whatever, that's what it is. Let's just add some stuff, right? Think about this. So what we're saying is the t-score is 7.127. How would we get that t-score? Remember, it's always our statistic minus our parameter, which is always based on our hypotheses, and then divided by the standard error. All right, and this year we have our notes, so you decide what you want to do with formulas. So statistic, that's from our sample. We're focusing on the means, but the thing is, we have 2 of them. So remember, anytime we have 2 samples, we focus on the difference. So if I have 2 statistics, I focus on the difference in them. Notice this gives me a positive number. That matches the fact that this is a positive t-score. If we subtract it in the other order, that's fine, right? That would change our hypotheses because our 1s and 2s would all be flipped. Right? You'd actually, yeah, whatever. But then, right, if we flip the order here, this would be a negative, so we should have a negative t-score. So something to consider. We assumed in the null, right, for our parameter, we assumed this is our sample difference. We assumed the population difference in means was 0. And then in the denominator, we've got square root, right? It's this formula, square root, like sx1 squared over n1 plus sx2 squared over n2. So we've got 34 squared over 110 plus 29 squared over 100. And so this, in this red box, really the blue numbers, that's how we produce that t-score. All that aside, once you, maybe on the exam, maybe a good idea is once you do the math stuff on your calculator and you get your p-value, go right to your conclusion, because that should be pretty automatic for us at this point, right? Same deal as always, reject or fail to reject, compare a p-value to an alpha, right? Whatever there is not evidence of the alternative. Had I made a mistake, right? Had I not recognized my mistake and had the wrong p-value, sure, I'm gonna lose points for my math section because it's not consistent with my hypotheses. That was my error. But I could still get full credit if I if I write a correct conclusion based on that theoretically incorrect p-value. So here we go. So conclusion-wise, p-value, right? So here's why, right? It doesn't matter that they didn't give us an alpha level. This p-value of 8.4 e negative 12, right, which is scientific notation. So like 0.1184 is below any common alpha level, or maybe you say below an alpha level of whatever, 1%, 5%, 10%. Maybe just pick 0.05 all the time if they don't give you one, right? However you want to say it. So you can do this, right? You can do what's in italics or parentheses, whatever you prefer. P is lower than alpha, we reject the null. So we reject the null hypothesis. Reject the null, that means we're throwing out that original assumption, right? We're rejecting the assumption that a person was innocent, so we think they're guilty. Or here, we're rejecting the idea that the two means are the same, so we think there is evidence. And now I'm just going to copy a lot of words. And again, sure, it's tedious sometimes, but it's going to be perfect context, right? So all I'm going to say is there is evidence that those who receive the new procedure, right? Yeah, for real, all this, all that stuff. I'm going to write all of that. The most critical thing is this, right? This test is about comparing means. So if you didn't have this on average, if you left that out, that's a devastating error to your conclusion. How do I avoid that? Don't be like, oh, it's too many words to copy. Just copy the freaking words out of the context. Sorry, I got really fired up there. So there is evidence that those who receive the new procedure will have less recovery time from the surgery on average than those who receive the standard procedure for patients similar to those in the study. I'm not really sure what happened here, but you know, whatever. That's it. Perfect conclusion. All right, let's see what we got. So this one I thought was interesting how it was scored. It was scored in a few sections. So section 1 was part A. So section 2, parameters are defined correctly. Those were those mu's with our 1s and 2s or our n's and s's. Hypotheses imply equality in the null, correct direction in the alternative, right? We did that on paper correctly, then I messed it up in the calculator, then I fixed it in the calculator. Correct test identified by name or formula. We actually did both. Correct test statistic, that was our t-score. We're good there. So there's another E for us. And then section 3. So this section 2 kind of lumped together the hypotheses and the math. Section 3, reference to an approximately correct p-value consistent with our t-score and our alternatives. So that's like I was saying, right? Never mind. Justifies conclusion based on size of the p-value. We said it's lower than alpha. Correct conclusion, we got that. So there's another E. And then notice here, if 3 sections are scored E to get a 4, you would have to check the conditions, right? So that was kind of weird how this was scored to me. So as long as we check the conditions, oh, I don't think there's 2. Both conditions, right? So like as long as we checked, I think it was randomization and large enough samples. I believe those were the 2 that you had to have. Right, we get an E. We obviously checked all the conditions. And then notice if you didn't check the conditions, you could only get a 3 out of 4. That's it. Next time I see you, we'll talk about number 5. And then the time after that, we'll wrap around back to number 1 and do some regression and then do some practice exams with College Board and just keep practicing. All right. Peace.